Hey pre-calc, how's it going? We are about to start our next lesson. This is lesson number 4, I think. But before we begin, I wanted to show you my grand quarantine purchase, and that is my nice rainbow array of gel pens. So most of my others are sitting in my desk at school, and I can't get to them. So I'm excited for some new colors. If you have a color that you're just dying to see the notes taken in, message me and I'll see what I can do. I think we're going to start with a nice dark pink. I tend to like the pink, so sorry if that's not your favorite. But here we go. We've been looking at arithmetic sequences, geometric sequences. Now, not all sequences are either geometric or arithmetic. Some are neither, but ways to categorize those. And we're going to take another step today and talk about a series. Series and sequences are related, but there are some distinctions in that. And so the first thing we need is a definition of series. And a series is when you take the terms in a sequence and you add them up. So a series is the sum of the terms in a sequence. So you're adding them up. So let's look at a couple of examples. Here is a finite sequence. 2, 4, 6, 8. Who do we appreciate? All right, 2, 4, 6, 8. That is a sequence. Notice it has 4 terms, definitely has a pattern. You are adding 2 each time, so it is an arithmetic sequence, but there are only 4 terms. If I were to look at the series would be 2 plus 4 plus 6 plus 8. That would be the series, and that series actually would have an exact sum. It would be 20 because 2 plus 4 plus 6 plus 8 is 20. But the series is when you add them all up. The sequence is just looking at those individual terms. Now, I can remember back in high school when I first learned about sequences and series, I had a really hard time remembering which term referred to which. Which one do you add them in? I was never a huge sports buff. I've increased my sports knowledge since marrying Mr. Mac because he is a big sports fan. But we always watched the World Series every year in my house. And so that helped me think about these definitions. In a series, you add them up, much like in the World Series. In order to win the series, you have to have accumulated games. Like you need to win 4 of those 7 games. And so those games have to add up to give you that victory. So that's just how I went about remembering which one, sequence or series, meant. Add them together. Maybe that'll help for you too. So this is a finite sequence. This is a finite series. You can also look at, here we've got an infinite sequence. It goes on forever, and you can have an infinite series as well. For plus 8, plus, whoops, I shouldn't have that piece, plus 12, plus 16, plus all of those pieces. And if you go to actually add those all up, you would be at a sum of infinity. That will just be infinitely large there. But watch what happens. You can also have a geometric sequence. This would be a geometric sequence. We're taking half each time. And if I add those up, I'm adding a smaller amount each time. And so this geometric series, not every geometric series, but this one, because the terms are getting smaller, actually has a finite sum. It approaches a certain value. And so that's some of the things that we will be studying as we investigate series. How do you find that sum. But before we get to infinite series, we're going to look at partial sums. Okay? A partial sum is, by definition, the sum of a specified number of terms. In a sequence. So it can be an infinite sequence, but we only want to know the sum of a few terms. One of the ways that we can designate that is with a capital S. Isn't that nice? Capital S for sum, and then a subscript of n, S sub n. So here in this first one, we're going to look at this example right here, number 1. We have a sequence, and we want to find the sum of those first 7 terms. Well, here's the first term, plus the second term, plus the third term, plus the fourth term, plus the fifth term. Well, I've got to get up to 6 and 7th terms there. So I better figure out the pattern here. It looks like I'm adding 4 each time. So this would be plus 22, and this would be plus 26. And so if I throw all of those in my calculator and I add those all together, it becomes 98. So S sub 7 is actually 98. Add the first 7 terms. That's a partial sum. Okay, let's take a look at the next one. I'm going to skip number 2, but let's look at number 3. I want the first 10 terms. Why am I picking these examples? Because they're not all arithmetic and they're not all geometric. We need to remember that we can have some other patterns. Can you recognize this sequence here? 1, 1, 2, 3, 5, 8. This is that famous Fibonacci sequence. 1 plus 1 is 2, 1 plus 2 is 3, 2 plus 3 is 5, 3 plus 5 is 8. I want to add the first 10 terms. So here's 1, 2, 3, 4, 5, 6, 7. That's 5 plus 8 is 13. 8 plus 13 is 21. 13 plus 21 is 34. How many? 1, 2, 3, 4, 5, 6, 7, 8, 9. I need one more. Plus 55. That's going to be my partial sum. S sub 10. If I add all of those together, that gives me 143. There's my partial sum. All right, let's look at one more. A sub n equals n cubed. That is not geometric. That is not arithmetic. But I can still work to find the first 5 terms. The first term, I'd plug 1 in. That would be 1 cubed. Then, second term is 2 cubed. And 3 cubed. 4 cubed, and 5 cubed. Now you can simplify those if you like into 1 plus 8 plus 27 plus 64 plus 125, or you can just put it in your calculator just like that. Either way, S sub 5 is going to be 225. Those are partial sums. And so that's one notation for you to see there, capital S sub n. But there's another way to look at sums. What if I don't want the first 10 terms? What if I want like the 3rd term to the 8th term? Is there a way that I could figure that out? You could work to figure that out in your partial sum formation. Take some subtraction there. I think you could probably figure that out. But there is another way, and that is this crazy Greek way using summation notation. So we can use represent a series. Remember, a series is just adding the terms of a sequence. We use the Greek letter sigma. That's what this is. It is a capital sigma and sigma for sum. And so this notation tells us to add the first 5 terms. Look, it says, hey, start with term 1. Remember, n is our term number. And so I'm starting here is the first term number. It does not always start with 1. It starts with whatever that number there. If I wanted to start with the third term, n would equal 3. But that's where I'm starting. And then this number up top is where I'm finishing. So this number up top will always be larger than that number down below. This is the last term number. So I'm going to start with term 1, and I'm going to go consecutively, adding 1 each time until I get up to the 5th term. This right here, that is the explicit formula for the sequence. That's how we figure out what each term value is. So this is saying whatever the term number, I'm going to multiply it by 2. So let's actually find the sum of this series. We're going to write it out. And so I'm going to want to see that, those terms written out. I'm going to start with 1, plug in 1. 2 times 1 is 2. I'm going to add to it. This is going to increment by 1. So next I'm going to have the second term. 2 times 2 is 4. And again, this increments by 1. And so next would be the n equals 3. 2 times 3 is 6. And then 2 times 4 is 8. And then 2 times 5 is 10. And I know to stop because I'm at n equals 5. And this was my maximum n value. So here is my series, 2 plus 4 plus 6 plus 8 plus 10. So this whole piece, that sigma notation, equals 2 plus 4 plus 6 plus 8 plus 10. And that equals, let's see, here's a 10, here's a 10, here's a 10. There are 3 10s in there. It equals 30. So that is summation notation or sigma notation. Let's try another example of that. Let's look at number 11. Notice here, I'm starting at the second term. I used a different variable. That's okay. K equals 2 to 8. I'm going to start with the second term, and I'm going to go to the 8th term. So here's my explicit formula. This equals, plug in a 2, and 2 squared is 4, minus 2, plus, increment that 3. 3 squared minus 3, 4 squared minus 4, 5 squared minus 5, plus 6 squared minus 6, plus 7 squared minus 7, plus 8 squared minus 8. All right, and I'm just going to do a little simplifying because I think this is actually kind of interesting. This is 2. This is 6. This is 12 plus 20 plus 30 plus 42. Notice here, just explore the patterns a little bit here. Notice this is 1 times 2. This is 2 times 3. 12 is 3 times 4. 20 is 4 times 5. 30 is 5 times 6. 42 is 6 times 7. That is really interesting. Why is that? Well, look back at your explicit formula, k squared minus k. If I factor a k out of there, I've got k times k minus 1. So for the first term, well, the second term, because that's what we started with, that would be 2 times 1. And then for the third term, that would be 3 times 2. That's where we get those. For the fourth term, 4 times 3. Fifth term, 5 times 4. And you can see those patterns coming out. And when we add them all together, we get 168. All right, I just want to look at one more example with you. I don't know that we might finish it, but just look here. You can get a little bit more congested. There are different things that you can do with this. Notice here's the sum, the sigma notation, and then I'm multiplying it by a constant. So all of our operations mathematically still work with that sigma notation. So if I were to look at this, I'm going to have negative 9/4 times this quantity, this huge sum. And I'm going to start, here I've got j, start at 1 and go to 6. So the first 6 terms of this quadratic sequence. Plug in 1, 2 times 1 squared is 2, plus 7 is 9. Plug in 2, 2 squared is 4, 4 times 2 is 8, 8 plus 7 is 15. 3 squared is 9 times 2 is 18, plus 7 is 25. 4 squared, 16 times 2 is 32, plus 7 is 39. 4 squared, nope, I already did that one. 5 squared, 25 times 2 is 50, plus 7 is 57. And last term, because we're going up to 6. 6 squared, 36 times 2, 72, plus 7, 79. Now you could throw all that into the calculator as it is, or you can think about this sum. Adding all of those together, you get a sum of 224. And then we want to multiply that by negative 9/4. And that becomes negative 504. So watch those different explicit formulas. Make sure you're following order of operations so that you are getting a correct partial sum. All right. Those are the examples I have for you. What I would like for you to do for homework is just finish the rest of the problems on the notes. So that means in this first page, going back and finishing 2 through 8, and then finishing through number 16 here. I look forward to seeing your work.